you. Thank you for Dominic and Ashish for giving me this opportunity. And thank you everyone for making it to the first talk. 8 in the morning, 8:30, first day. Okay, so I was really excited to see this workshop and because I have been doing something along how can we use social choice theory. There's rich literature on social choice theory to do something fairness about fairness in machine learning. And so in particular today, I'm going to focus on federated learning because that appeals quite a lot to social choice theory. So the setup is this: you have a set of agents with data. You can think of them as clients, hospitals, and so on, and they want to learn something together using everybody's data, but they don't share it. Like hospitals wanting to learn to diagnose, but they don't share the data. And there is this really remarkable, powerful framework of federated learning, which says that, okay, there will be a central planner, if you wish, from a social choice theory terminology, who will try to help them learn without sharing the data. And they will not even share the data with the central planner. So what they will do, central planner will decide a classifier, it'll tell them, and these guys are going to tell the central planner how good they like it, as in they'll just send the gradient of their loss functions to the central planner. So here I'm assuming somewhat of a machine learning terminology. Are we all okay with that, or should I brush up on that? Okay. So yeah, everybody has a loss function based on whatever data they have and whatever they want to learn. And once they know that, okay, this is the classifier, then they know the what the loss is or what the gradients is. And then the central is going to modify the classifier, propagate again, and so on. Just keep going until it converges to something. Now, lots of uses you can imagine, right? Like, and this is one application slide. Like in hospitals, they want to learn together to diagnose without sharing the data. Smartphones trying to learn to autocorrect or complete sentences without sharing the data because everybody uses different type of lingo. So it might be relevant and so on. Self-driving cars and so on. So formally, the model is you have n agents, each of and there is a set of classifiers. Each agent has a data set and a loss function. The loss function is going to be a function of classifiers and the data that they have. But then I'm going to assume that the data set is fixed for now, so it's not changing. Okay, so essentially the loss function is a function of the set of classifiers. And the goal is to learn a common classifier, say theta, using everybody's data, but indirectly. And there's a rich history started, I think, if I'm not mistaken, I'm not a machine learning person, but started with Google in 2016. And so their basic idea is going to be, they start with some theta, and the update to the theta is that they get the gradients and they do the weighted update to the theta. And the weights depend on your data size. How many data points do you have? That's how WI is proportional to the number of data points you have. So more the data, the more the weight you have to your gradient. And that's kind of natural. And Fed average does something smarter than Fed SGD, where you have more client-side updates and easier way to do. I'm not going into detail into that, because that's not relevant as much. The point was that extensive work on that since 2016 was very important. But very soon they noticed that there are fairness, privacy issues. Although the primary motivation was to privately share the data, it is not privacy preserving, and there are also a lot of work on privacy preserving federated learning and so on. Yeah, so, and also not strategic proof. And so this was already observed, and there were a lot of works on this, and there are different notions of fairness defined and tried to achieve them. One obvious kind of notion is egalitarian, minimize the maximum loss. Makes fun. Another was proportional they call it proportional. It's somewhat like an equity-based fairness. I'm going to use proportional word for something else, so that's why I'm slashing it with equity-based fairness. And also there are a lot of work on like equalizing the errors. That's kind of equity-based. So here NIs are again the number of data points the agent's I has. And or you can try to equalize the two positive rates or two negative rates or loss or whatever functions, right? But equalizing some kind of loss of everybody. Now, if you notice from a game theoretist perspective, if there is one agent who is noisy or adversary with lots of junk data, what's going to happen to all of these functions? So the first function, which is trying to minimize the maximum loss, this guy is going to have the maximum loss, right? So it will be probably forced to cater to this person. Yeah. The second one also, again, if this person has a lot of loss, then it will it will not be able to optimize for others because this guy has a lot of loss. So if you try to equalize everybody's losses to this person's loss, then how do you just make it do a justice to others, right? So that's one issue. So I mean, this beautiful work set of works on this was obvious. I mean, they were assuming that everybody is nice, and then how do we do the fairness? And that's a very valid question, right? But if that's not the case, then things can go bad for the other people, right? So then we started thinking that what can we do here? And SCT, right? Social choice theory has lots of beautiful notions here on fairness and on strategy proofness and so on. Can we bring them here? And so first thing, what is the setting that it matches the best to in social choice theory? And you can immediately see that it's a public decision. Yeah, because they set of agents, they set outcomes that among which they are trying to pick. So together that they are trying to pick one outcome. Yeah. And once they pick the outcome, there's some loss which is equivalent to some utility. There's some high value minus the loss. Yeah, so exactly fits the public decision making very nicely. And again, in public decision making, you want to pick a common outcome that is liked by all. And now you can define what do you mean by liked. And one really nice notion of fairness where Kamesh and Ashish also have the works, and Nisar, and I think Fain is Kamesh's student. Yeah, is the core, right? And the core of notion of core in public decision making was already there, but they applied into relevant setting into computer science and discrete allocations and so on. So what's the notion here? So as soon as we talk about core, we have to talk about blocking correlation. So you have an outcome, and some set of people say that we are not happy. That's called blocking correlation. So, okay, so what do they say? Okay, they say that there exists another outcome that we like better. So ideally, you would want that like better means it's Pareto dominates for these agents 2 theta star, the outcome that you are proposing. Yeah, but do you think this is possible at all? Like hospital building in a neighborhood in your city, you will say I want the hospital next to my house. Yeah. And I will say, I want the hospital next to my house. There is no way you can pick an outcome that makes everybody happy. Yeah. So you have to think of it like, okay, you have some social capital with you. Okay. You can change the decision only up to your social capital divided by total social capital of everything. Yeah. So if this is fairness, so let's say we give equal social capital to everybody. So 1, 1, 1, 1, 1. Then set of S agents has total social capital of size of S. Yeah, and total social capital of everybody is N. So that's that much changing power you have. So that much utility loss you have to, or if you could just multiply that with that ratio of the fraction of social capital you have, then you should not be able to change. Does this make sense? Because this is not exactly core in the sense of private good setting. This is a public good setting, right? So you have to do this scaling. Okay. And then core is where there is no blocking correlation. Okay, so any question about the notion? Okay. So immediately you can see that it's proportional in the sense of pair division type kind of thing. So what does that mean? Every agent gets, if there are n say agents, then every agent gets the utility is at least the maximum utility they can get divided by n. Okay, so if everybody were kind of equal, you're kind of saying that everybody has an equal social capital, so you should get at least maximum possible divided by n. It's Pareto optimal because when S is or the entire set, then there's no other outcome that is better for everybody, right? So it's Pareto optimal. And somewhat robust, because if there is one adversarial agent or very few adversarial agents, and there's a large number of very good agents whose preferences are aligned somewhat, yeah. Let's say hospitals trying to learn something, but there is one adversarial agent trying to harm them. This one agent will not be able to harm them because their preferences are aligned, and so they will be able to, their coalition does not want to deviate. It's a large coalition, they have a large social capital. So they must be very happy in their finding. And so we first considered the existence in the setting, and we saw that if you consider this function, which is look like a weird function, and it's not even a function, it's a correspondence. But if this is convex for every theta, then it exists, and you can guess that it's through the fixed point theorem. I show that the fixed point is in the core, and then apply Kakutali's fixed point theorem to the correspondence. So, so if UIs are concave and loss functions are convex, then indeed phi of theta are going to be convex Z for every theta. And in the machine learning setting, it covers quite natural learning setting like linear regression, logistic regression. So let me give you a quick proof of why this is in the core, and these ideas were kind of present in the previous two papers of Kamesh and Ashish. So suppose you have a fixed point. That means you have a theta star, so that P of theta star contains theta star. That means it's the argmax of that function. So if you replace in here theta star for both of them, then this quantity is n. So that's the maximum possible value, right? So that means for every theta, this ratio summation is at most n. Now, if this guy is not in the core, then this must be a blocking correlation. Blocking correlation meaning there is a theta that everybody likes up to this scaling factor. Yeah. And there's at least one strict inequality. You get the ratio, the lower bound on the ratio. When you sum up these ratios, there are S agents, so S and S are going to cancel, and you're going to get that this is strictly greater than n. And the other quantities that you add here is not going to be negative, or everything is positive. So then it contradicts the fact that it has to be less than equals 10. And this is one quick. And then next, we show that you can compute it if you can find the maximum of this function, sum of the logs. And this appears time and again, right? This is a Nash welfare base. So again, yeah. So this is in the core. And again, the proof is first you show that whatever is the maximizer will satisfy the first condition that for every theta, the sum of the ratios at most n, and then we just saw that if that is the case, then it's 4. And again, I would kind of repeat that these ideas in different settings were present in both of these papers. Finally, okay, you can find it in a central manner, but can you find it through a federated learning protocol? And we show that yes, you have to make a small bit of tweak in the protocol. You still ask for the gradient of the loss, and you also ask for the actual loss value. And then if you look at the gradient of this function, is exactly gradient of the utility divided by the value of the utility. That is exactly gradient of the loss minus minus of the gradient of the loss, or the summation should have been the outside, sorry. And divide by h, because that's how I define the utility. So we can get this. But immediately, like a typical machine learning person would object that now we are in Gen AI model, deep neural nets. Yeah, nothing works without deep neural nets. So what happens in that case? Well, in the worst case, I'm a theoretician, right? So I always think worst case. So if you pick deep neural net, then what kind of loss function do you have? Neither convex nor concave. Yeah, it's a hilly, it's a hilly terrain. Yeah. So then, and if you do any federated learning, this type of protocol, you're going to end up in a local optima, approximately local optima. Okay, what can you say about that? We can show that it is an approximate local core. The guarantees, to be honest, are not great that a theoretician would want, but that's what we get. And then we ask, can we do better? And in the worst case, no. Because you are asking for too much, right? From the theory perspective. So if you're utility two agents with this very different utility function, that their match where they is very low, right? Like there is no classifier that both of them like reasonably, then what can you do? You can't get even proportionality guarantee. No approximate proportionality guarantee. You can imagine, right? You can create utility functions that you can't get any proportionality guarantee either. So then we said this is not satisfactory. Yeah. All deep neural nets are not going to give you these weird worst case utility functions where you can't even give any approximate proportionality guarantee. Typically, most of them are going to be, okay, hilly, but like there are results, right, that most of these local optima are reasonably good enough, and if your preferences are aligned, they're going to be aligned. So in that case, what do you do? So we moved to the ordinal setting. I think I have this. Okay. We moved to ordinal setting. We said, okay, if we start talking about utility function and still want worst case guarantee, don't expect anything. So what about ordinal setting? Because ordinality is going to capture that, okay, you have this optima, then you have this optima, then you have that optima, all different like non-convex set of optima, but they are nice. Yeah. So when I put them in a sequence in my preference order, they're going to be together there. Yeah. So in that setting, how do you define? We took or we tried to define it, and then we came across the smallest paper, last paper. Little late, but not too late. Because we could only define proportionality, he defined the entire. So okay, so the definition of core in the ordinal setting is intuitively the similar definition to the core in the utilitarian setting. But if I directly tell you, the definition is too windly. Okay? So I'm going to do it slowly. Okay, I'll go from utility to ordinal. So given the preference of the agents, there are m classifiers, finite, so his setting was finite. Let's think of also in our minds, utility corresponding to each classifier. Okay, saying the first one has utility m, the second has m-1, the last one is 1. Okay, this is just imagination. Now, under the utilities, what is the proportionality? You should at least get maximum divided by n. Maximum is m. So every agent should get at least m over n. Yeah, that's a proportionality. Yeah? Okay. So now we say that, because we have to define blocking correlation, remember, to define core. So now we say that this one agent is going to block this theta star if the agent gets less than m over n. What does that mean in terms of ordinal preferences? Well, it is basically saying that what is UI of theta star? You have to look at the position of theta star in this order. So how many classifiers are better than theta star for this agent? Let's say B is that. Then what is this saying exactly? It is saying that m minus size of B, that's a UI of theta star, should be, if that is less than m over n, then I lost theta star. If you do the math, m is size of B. the set of number of classifiers. M, if you take out M, then M and M are going to cancel from both sides, and you get this condition that 1 minus size of P divided by size of P is less than 1 over N. Now, this is purely in terms of ordinal preferences. There are no utilities around it. Okay, so we say that you output theta star, and agent I, one agent blocks this theta star if 1 minus P over size of P over size of P is less than 1 over N. 1 over N is the social capital of this agent. Okay, and B is the set of classifiers that is liked by this agent more than theta star. Okay, I'm going to extend that immediately to set where the left hand side remains the same, the right hand side is just the social capital changes of set of agents. Yeah. And what is B? B is the set of classifiers that is liked by the largest set of classifiers that is liked by all of them more than theta star. Okay, make sense? Yeah. And of course, if no broken correlation, then it's called V2. Okay. Now, our machine learning setting is a continuous setting with non-convex, non-concave utility. Yeah. So we have to go much, extend it much more. So then we go to directly to measurable sets. You don't have to be convex or anything, just measurable. Let's say lambda is the measure, and utility functions have to be measurable. Just think continuous is enough. Okay. We're going to exactly mimic the definition, except for the sizes. Now we have just the measures. That's it. Okay. And again, B is the largest set of classifiers that is liked by everybody. More. Now, more, what do you mean by more? You have greater, it's like Pareto dominant. Greater than or equals for everybody, at least for striking. Yeah. And again, I have an epsilon there because of the continuity. You can't get it. I should not say can't, but we couldn't get exact. So you have to have some little bit of leeway there. And that's why we need some epsilon there. And if, yeah, no block of correlation here. And so this gives us a new setting in SCT to study from the pyramid. Yeah. And our results are that it exists, okay, for this general case. And you can see that, again, you can show that it's Pareto optimal, approximately Pareto optimal and proportional. And it gives better guarantees when the preferences are aligned. And I can tell you about these more offline. And there are lots of questions in this regime. What about computation for V2-4? What about if we had agents have limited heterogeneity? How do you define, first of all, what that means? And in that case, can we give better guarantees than just the social capital of size of S? Yeah. And so on. Also, the strategic analysis. What if agents are strategic? Can one agent report something weird and gain? Yeah, in the federated learning protocol or in some other way. That was leading me to another set of works on strategizing on data sharing. You can think of the FL as a game where agents share data. Yeah. And how much data, the strategy is to decide how much data to share. And we had a bunch of results there, but I'm going to skip in the interest of time. And I can talk to you offline about this, or you can go to Aniket's poster on Thursday for more. There are a lot of questions there. That's why I wanted to talk about that. But yeah, well, offline. Thank you, everybody.